the last lecture, we have started analysis of distribution system, and we have started with load flow studies. Last lecture we have seen one algorithm which is called as backward forward sweep algorithm, which is classical algorithm of load flow studies in distribution system. Initially what I did, actually I introduced algorithm with simple example, and after that we have seen step by step algorithm of basically backward forward load flow. Let us see what we have seen. So, we have seen that if there is a distribution system, let us say your distribution system is like this. You are having this distribution system here, there are various buses, say these are actually, there is one branch here, bus number 1, 2, 3, 4, 5, and say this is bus number 6. Bus 1 voltage is fixed at say Vs angle 0 degree, and in this case we can write your current equation Ij at any kth iteration will be equal to PLj plus j QLj divided by Vj, which is basically phasor, and then you have to take the complex conjugate of it, and then it will run for j is equal to 2. In this particular case it will run up to 6. So, using this we can get the load currents of each bus starting from bus number 2 ending with 6. And then we have seen that in case of backward sweep, we are calculating the branch currents. So, in this case you have already calculated these load currents, which are basically say I5, I4, I6, the load current is here say I3, and here say I2. So, this all the load currents are calculated in this step. Then in backward sweep we can calculate the branch currents. So, we know that we have to start from end nodes and we have to go towards your source node. So, we will start with this end node as well as this end node here, the node bus number 6. So, say I4 phi will be equal to I phi. So, current into this branch will be just I phi current. So, I4 phi will be just I phi. Now, current I34 will be equal to this current, which is between I4 phi plus I4. So, it will be I4 phi plus I4 already calculated, you can use it here. Then I36, current I36 will be equal to I6, because in this branch only I6 current will be flowing. And then we are calculating I23, which is basically current into this branch, will be equal to current which is flowing in I34 plus current which is flowing from I36 plus current at bus 3, which is I3. So, here I34 and I36 we already calculated before that, and then I12 will be equal to I23, basically this current which is flowing in this branch, plus current load current at bus 2. So, these equations we can have in backward sweep, which will give basically line currents in all the lines. And then we have seen in forward sweep we need to calculate bus voltages. So, in forward sweep we calculate bus voltages. So, explicitly if you write, your bus voltage V2 will be equal to bus voltage V1, which is Vs angle 0 degree, which will be fixed, minus your Z12 into I12, which you have calculated it here. So, V1 is fixed, I12 is also calculated, Z12 impedance is known. So, we can get voltage V2. voltage V3 will be equal to voltage V2 minus Z23 into I23. I23 is calculated, V2 is calculated before V3. So, V2 is also known. Then V4 will be equal to V3 minus Z34 into I34. I34 is calculated here, and V3 we have calculated earlier step. Similarly, you can get V5 will be equal to V4 minus Z45 into I45, and V4 is taken from here, and I45 already calculated it here, and then V6 will be equal to V3, because this 6th branch is connected to branch bus 3 here, 6th bus is connected to bus 3 here. So, it will be V3 minus Z36 into I36. So, I36 is already known, and V3 we can get it from here, which is calculated before calculating V6, because we are starting with source node. We are starting with source node, and then we are going on calculating the voltages till end node. So, voltage, when we are calculating voltage of V6, V3 will be already calculated, and then in backward sweep you have seen we start with end nodes and go towards forward nodes. So, in that case I4 will be already calculated before calculating I34, because this branch is actually end branch. So, currents in branch which are connected to the end nodes will be calculated first, and then we are going towards source node. So, this was basic philosophy of backward forward sweep algorithm. Detailed algorithm of backward forward sweep load flow we already seen in the last lecture. Now, let us see how we can use this algorithm for 3-phase systems, because we have seen that in many cases your distribution system is unbalanced one, and if you are analyzing unbalanced system, you have to do load flow analysis with full 3-phase system. So, you have to consider all the 3 phases during the analysis. So, let us see or let us consider simple 3-phase distribution system similar to this. So, you are having, see, these 3 phases, and say this is bus number 1, this is bus number 2, and then same 3 phases are extended till bus number say 3. So, here your bus number 3, and after bus number 3 say only 2 phases are extended, 3rd phase is ending here, and they are connected to node number 4, and say after this only 1 phase is extended, and here your bus number 5, and this phase C will be extended and connected to bus number 6. So, here so if you see, this will be bus which is basically I can call it 2A, this I can call 2B, and this I can call 2C. Similarly, this is 3A, 3B and 3C, and this 6 node will be having only 1 phase. Similarly, node 5 will be having 1 phase, and node 4 is having 2 phases. Now, if you see impedance matrix, so Z12 impedance matrix will be actually 3B by 3, sir, because all the 3 phases are there, and all the 3 phases are basically mutually coupled with each other. So, it will be having ZAA, ZAB, ZAC, ZBA, ZBB, ZBC, ZCA, ZCB and ZCC are the impedances of or impedance matrix of all 3 phases. Now, since these impedances are between node 1 and 2, I can just write this is 1, 2. So, all the impedances of 1, 2 will be like this. So, this is nothing but Z12 impedance matrix between node 1 and node 2. Exactly similar way I can write Z23, it will be also similar 3 by 3 size, However, I need to change only this index here, it will become 2 3, otherwise it will be same. And if it is having same structure, the same matrix can be used for this section also. However, if you see this section between 3 and 4, so in this case your Z 3 4 will be of 2 by 2 size. So, it will be Z AA, Z AB, Z B A, Z BB, and since it is between 3 and 4, I can just give index 3 4 everywhere. So, this will be impedance matrix between 3 and 4, this is how we have to write. And then impedance matrix Z 4 phi. So, Z 4 phi will be just, since it is having only one phase, it will be Z AA, now it is A phase. So, Z AA between 4 and 5, and then when I am setting Z matrix of 3 6, it will be again Z, however this phase is C phase, so it will be Z C C 3 6. So, we can see that depending upon number of phases present in particular section of the line, the impedance matrix will change. So, we need to use particular impedance matrix for particular section of this one. Similarly, if you see the voltages, so source voltages will be perfectly balanced, I can assume, and having equal magnitude. So, these will be Vs angle 0 degree, which is voltage of A phase, Vs angle minus 120 degree. So, I can say this is Vs A, Vs B, or I can say Vs A will be equal to Vs angle 0 degree, Vs B will be equal to Vs angle minus 120 degree, and Vs C will be equal to Vs angle 120 degree. So, these voltages will be perfectly balanced and they will not change during the iterations. Voltages of other buses will change during the iterations. So, what I will do actually, we will try to write explicit step by step algorithm for this particular system, so that we will understand how we can use it for 3 phase system. So, in this case again I am assuming any 3 phase generalized system. We already seen that how to get the impedance matrix. So, any generalized 3 phase system similar to earlier system, I can assume that it is having some branches here and then some branches are connected here. Any generalized system, say 1, 2, these are the node numbers, any jth node, say this is M, bus number n, and if say there are n number of nodes. So, total number of nodes are n into the system. So, total number of buses are say n. In this case also step 1 is initialization of voltage. So, explicitly write the algorithm. So, step 1 will be initializing bus voltages. So, we will initialize bus voltage. However, in this case there will be complete matrix of voltages. So, V A J, V B J and V C J, which are voltages of any jth bus at 0th iteration, because we are initializing it. So, I am just writing 0th iteration will be equal to, initially as I told you, we are assuming the voltages at this bus which are basically Vs angle 0 degree, Vs angle minus 120 degree and Vs angle plus 120 degree, which we are initializing for j going from 2, 3 up to all the buses, that is capital N. So, all the buses will be initialized to all the all the voltages with initial voltages which are VSA, VSB and VSC, which is equal to Vs angle 0 degree, Vs angle minus 120 degree and equal to Vs angle plus 120 degree. So, all the buses like 2, 3 and up to n will be initialized with these voltages at initial bus. And then we have seen step 2. Stage 2 will be initialization of iteration count and we are using k as a nomenclature for this. So, k is equal to 1 is initialization of iteration count, and then in step 3 we have seen that we need to calculate load currents. So, basically computation of load current will be done in step 3. However, in this case there are all the 3 phase currents. So, depending upon how many number of phases present, in a particular section, you need to get phase currents. So, I A j at kth iteration, I B j at kth iteration and I C j at kth iteration, which are basically 3 phase load currents, which will be equal to, it depends upon loading of this one. So, load P L A j plus j Q L A j, load of A phase and jth node divided by voltage of k minus 1th iteration, and then we are taking complex conjugate of it. So, this gives me the load current of A phase. Similarly, load current of B phase will be equal to P L B, real part of the load of B phase, plus J Q L B j divided by voltage V A j V B j at k minus 1th iteration, and you have to get the complex conjugate of it. Similarly, we can get P L C j plus J Q L C j, which is load at bus number C at jth bus, phase number C at jth bus will be equal to V C j at k minus 1th iteration, and you have to take the complex conjugate of it. It is actually k minus 1th iteration. So, after getting currents, we go for step 4, and step 4 we have seen that it is basically backward sweep, and in backward sweep we are calculating line currents. So, line currents, now there will be 3 phases. So, there will be 3 line currents here. So, I am an line current in A phase, I am n in B phase and I am n in C phase. So, we need to calculate all the 3 phases. Any branch I m nth branch, I can get I m n A, or I can write, instead of this I can just write I A m n, I B m n, I C m n. So, in this case also I A m n, I B m n and I C m n, which is basically currents flowing in 3 phases of mn section of the line, and it is again at kth iteration. So, I have to write iteration count k here, will be equal to, so we need to add the phase currents into this one. Again there are 3 phase currents. So IAN is phase current in A phase, IBN in phase current in B phase, ICN phase current in C phase at nth bus. So it will be IAN, IBN and ICN, all the 3 currents which are already calculated in this kth iteration. So these currents are already known, plus we have seen that summation. Now in this case there will be 3 summation of all the branches, all the currents of branches emanated from bus N and phase A. Similarly, all the currents of branches emanated from bus N and phase B. So all the branches which are connected to phase B which are going out of this, because we have seen that in N phase itself there may not be all the branches which are connected to next bus which is connected here, say MN O. So there is possibility that all the 3 branches may not be connected to O bus, and then in this case all the currents of branches emanated from bus N and phase C. So this will give you all the 3 phase currents of all the branches of this particular distribution system. So once you get the current, we should go for step 5, which is forward sweep. And we have seen that in forward sweep we are basically calculating the nodal voltages. So in this case nodal voltages VAN, VBN and VCN at kth iteration. So say this is this node N. So at this node the voltages, A phase voltage will be VAN, B phase voltage will be VBN and C phase voltage will be VCN. They will be calculated based on voltages of earlier node, that is voltage of node M, which is basically VAM, VBM and VCM. So these voltages minus voltage drop which is happening in this will give me voltages at M. So this will be equal to voltages at nth bus will be equal to voltages of mth bus, which is VAM, VBM and VCM at kth iteration. Because we have seen that this is forward sweep, we calculate voltages of this bus first and then we will go for this bus. So these voltages are already known, minus, now in this case it will be impedance matrix, and if it is all the 3 phases are present into this section, it will be 3 by 3 impedance matrix. So it will be ZAA, ZAB, ZAC, ZBA, ZBB, ZBC, ZCA, ZCB and ZCC. And since this section is mnth section, so I can say just write Mn everywhere. So this is nothing but impedance matrix of this line section here, and then this should be multiplied with your line currents which are flowing to this line, and we have seen that we already calculated these line currents in step number 4. So, these line currents will be AMN, IBMN and ICMN. At kth iteration we already calculated. So, this will give me voltages of nth bus after completion of forward shift, and this will be for all n which is starting from 2, 3 and up to n, and this loop will be done for all branches. This will be done for all the branches, and this will be done for all the nodes. So, this is how we get all the nodal voltages, and then we have seen that step number 6 is to get the errors of the voltages. Now, here there will be 3 errors. So, error of the voltages of jth bus in kth iteration will be equal to max of. So, first you have to calculate the at jth bus there will be 3 voltage. So, if you are considering, say this is your jth bus, so you will be having VAJ, VBJ and VCJ, 3 voltages which are calculated at kth iteration as well as k minus 1th iteration. These voltages will be available. So, by taking the difference of particular voltage, so it will be VAJ at kth iteration minus VAJ at k minus 1th iteration. This will be one error in A phase, then error in B phase, so you have to subtract the 2 iteration voltages, that is kth iteration voltage of B phase and kth iteration voltage of k minus 1th iteration voltage of B phase, and then third VCJ at kth iteration minus VCJ at k minus 1th iteration, and mod of it you have to take it, and maximum of it, maximum may be coming in A phase or B phase or C phase, will be nothing but error in voltages of say jth bus. So, this will learn for j is equal to 2, 3 and it will go up to n. So, we will get errors in bus voltages, maximum error in bus voltages at each of the bus, and then step 7 will be similar to our algorithm. So, E max of kth iteration will be equal to your max of E1 kth iteration, E2 kth iteration up to En at kth iteration. So, here all these values E1 it will start from 2. So, E2, E3, E4 at kth iteration. So, this E2, E3, E4 they have already calculated in step 6, and we are getting the maximum errors by calculating the max of it. So, these are nothing but errors of the voltages at particular bus, and getting maximum error will get maximum error, it might be happening at any bus into the system, and once you get the maximum error in step 8 you have to compare this maximum error with respect to your tolerance value. So, E max at your kth iteration will be, if it is lesser than your epsilon which is tolerance which is given, if this condition is getting high. So, there you have to use if statement here. So, if this is true, you have converge, then print the results and as well as store the results, and else if this condition is not satisfied, means E max is still more than your tolerance value, you have to update iteration count k is equal to k plus 1, iteration is updated, and go to step number 3. So, if this error is more than your tolerance value, you have to go to the step number 3, where by using the voltages of earlier step you have to get the currents, and from the currents, load currents, you have to get the branch currents using the backward sweep starting from end node and moving toward the source node. You will get all the branch currents, and once you get all the branch currents, you can use which is called as forward sweep. So, starting from your source node, keep on getting the voltages till your end node by using step number 5, and once you get the voltages, compare the voltages of this iteration with respect to earlier iteration for all the 3 phases here, and get the maximum deviation at one particular phase for that particular bus, and then calculate maximum error at all the buses. So, this will give you what is called as the maximum error for all the buses, and then compare this maximum error with respect to your tolerance value, which may be 0.000001. If you are using per unit system, this will be sufficient, and then if you are comparing this, if the error is lesser than this tolerance value, you can say you have converged with algorithm, print the result, otherwise again a iteration count and go to the step. So, you will keep you will be in this loop till your algorithm converges. So, in this particular lecture, we have seen backwards forward sweep algorithm applied for radial system, but unbalanced system. So, we have seen that whenever unbalanced system is there, we have to consider all the 3 phases. So, we have seen how to use this backward sweep forward sweep algorithm for full 3 phase system where all the 3 phases are considered. Here I have introduced you to concept where we have seen what are the impedance matrices for different sections of the line and how they are defined, and after defining your impedance matrices, we have seen step by step algorithm for 3 phase backward forward sweep algorithm. Next time we will see another algorithm which is based on direct approach. In that case we will see how this process of backwards forward sweep is simplified and effectively used. Thank you very much.